Vector Laser Projector by Larry Cressy, Georgia Institute of Technology, Electrical and Computer Engineering Department. My name is Larry Cressy. I'm a fourth-year electrical engineering major, and I've completed 7 total semesters at Georgia Tech. I work on personal projects like this laser projector, and I enjoy working at the campus makerspace in my free time. I constructed a DIY laser projector. It projects lasers in patterns that can be controlled programmatically. The purpose of this is to render images, arcade games, and anything else you'd want to render in line art on the wall using lasers. A goal of the device is to provide a good experience for viewers. It requires a variety of interlocking systems that work together. So this laser projector consists of many distinct but interconnecting systems. There are power supplies that deliver power to various systems, driver boards run actuators and lights, and control boards orchestrate the whole operation. There are 2 control boards, and each has its own microcontroller. The projector output has 5 degrees of freedom: laser color, red, green, and blue, and laser position in X and Y. In that way, we can control the laser to show any color and draw any shape. There is a user interface that allows the user to control the laser projector, and a pass-through that allows the PC connected to the laser projector to control it and running its own custom laser show. In my opinion, the most interesting part of this project is the hardware. There are a bunch of parts that need to work together in order for this thing to work. Included in this list of parts are power supplies, which power all the various other components, galvanometers and galvanometer drivers, which work together to aim the laser around, lasers and laser drivers, which of course is the source of the light for this projector, the main controller board, which is kind of the brains of the operation, the interface board, which tells the main controller board what to do and allows the user to control the thing shown by the laser projector, and to debug errors and select the operating mode. There's a chassis and thermal management system, which is often overlooked but is one of the most important systems in maintaining the safety of the device. Previous prototypes have combusted due to lower amounts of attention being on this topic than should have been. First, we have the power supplies. There are 2 DC to DC converters that convert the 12-volt main power rail of the laser projector to plus or minus 15 volts. This bipolar supply is used for the analog circuitry on the main control board and for the analog circuitry on the galvanometer drivers. Each galvanometer driver has its own power supply. Previous iterations of this project used one power supply for both of the drivers, but this was found to make the power supplies hot enough to melt their own solder, which is bad. The galvanometer drivers are important components as well. These off-the-shelf modules drive the galvanometers. They receive ILDA-compliant control signals from the main controller board. These ILDA control signals consist of 2 complementary PWM signals. Each signal has a range of 5 volts. The positive signal ranges from 0 volts to 5 volts, and the negative signal from negative 5 volts to 0 volts. These devices need plus or minus 15 volts to run their analog circuits, and this is, of course, derived from the power supplies mentioned previously. The galvanometers are one of the most important devices in the laser projector. They are electromechanical actuators that move a mirror. They take in power and drive signals from the galvanometer drivers. They are mounted so that a laser can reflect off 2 mirrors to enable positioning of a laser in 2D. As you can see, they are mounted at 90-degree angles from each other, so that the laser can come in here, reflect off of the x-axis, reflect off of the y-axis, and then be directed within a 2-dimensional plane on the wall here. Of course, you can't have a laser projector without a laser. This one's no different. The laser generates the light the projector beams. It actually contains 3 separate lasers, one for red, one for green, and one for blue. The total power of this device is 500 milliwatts. 100 milliwatts for red, 200 for green, and 200 for blue. All combined, this is a class 4 laser, so avoid aiming at your face and eyes to avoid injury. An additional system being developed for the prototype consists of a thermal imaging camera aimed forward at the direction that the lasers are being projected at. If this device detects any heat, it can assume that there's a person there and that it's time to shut off the laser to avoid injury. The laser driver is pretty important. It's the device that provides a constant current source for the 3 lasers. They can be modulated using a TTL pulse width modulation signal. This signal is generated by the main control board. Using this signal and this driver, we can change the laser's color and programming to virtually any color. The main control board is kind of the brains of the whole operation. It handles control of the lasers and the galvanometers. It generates an ILDA-compliant control signal for the galvanometer drivers using some op-amp circuitry. The main microcontroller is a Teensy 3.5, so chosen because of its onboard dual DACs. These digital to analog converters simplify the generation of this ILDA signal considerably when compared to a normal microcontroller without digital to analog converters. The interface controller enables the user to control the laser projector and debug errors. It has a clickable light knob and a big red emergency stop button. The light knob acts as an indicator light and lights up red in the event of an error. The emergency stop button is a critical safety feature for dealing with this powerful laser and immediately halts the system if pressed. It hosts a microcontroller, an ESP32, which has Bluetooth 5.0 and Wi-Fi capability. Future versions will use this capability to enable remote control of the device over Bluetooth or Wi-Fi. The chassis is an often overlooked component of the laser projector. It was wholly 3D printed in one piece at the campus makerspace. The device contains several case fans for active thermal management. Without this active thermal management, the device would soon become too hot and catch on fire or shut itself down. It has sensors to measure internal temperature and inform the main control board of how hard to run the fans. Without this system, of course, the device could catch on fire, so it's quite important that this system be retained. The external power supply is a pretty simple part of the project. It was salvaged from an old Dell server and is rated for 200 watts at 120 volts AC. The output voltage is 12 volts, which corresponds to the main system voltage of the laser projector. And that figure is an actual photo of this power supply next to a shape being projected by the laser projector. The software for this laser projector was written in C using the Arduino IDE. It stores a list of points and a list of colors, which the galvanometers aim at, and the laser changes color to match. The interface board updates a few small OLED displays to help the user see what is going on and debug potential errors. It's capable of passing through data from a PC, enabling a PC to control the laser show. There are 2 different random modes, sound reactive and random, that are used as demos. An open lanes pass-through, in which the laser projector is controlled using a PC. The PC can generate a laser show on the fly or enable it to show arcade games. In conclusion, the laser projector works and was a really good experience. It allowed the author to delve into various aspects of electrical engineering, from power electronics to optics to embedded systems and beyond. The author definitely recommends building one.